We're gonna discuss a strategy for solving some related rate problems, and then do a little bit of some examples. And hopefully, by the end, you guys will have a little time for some individual practice before you gotta go. And then tomorrow, you should be able to just work from home and be okay. So, all right. So, I think, like I said, the hardest part of this is like this first bullet we were discussing is getting the equation set up, because the differential stuff you guys did in the last section, you already had an equation to work with most often. It was like some kind of formula from geometry, or they just gave you an equation to work with. In this one, it really kind of depends on what they're asking you to do. And oftentimes it's going to be, is there some kind of geometric relationship, like look for triangles and stuff like that a lot, and it helps. So let's say we've got a ladder that's leaning up against a wall. And believe it or not, this is kind of like a classic related rate problem here. So there's our little brick wall. And let's say the ladder is 40 feet long. And we place it so that it is 30 feet from the wall. And that's all we got to go with. So, all right, so if the ladder is falling at a rate of 2 feet per second, at what rate is the ladder moving away from the wall? All right, so do you see how this is a related rate problem? There's a couple of rates we're talking about in there. I give you one, I'm asking for another one. Okay, so first of all, let's make sure that the geometry of the problem makes sense, just like the physical, what's going on. So if this ladder starts to slip on the wall, okay, do you see how the top of the ladder then is going to go sliding down the edge of the brick wall, right? If the ladder holds its shape, the base of the ladder should be moving out away from the wall, right? It would have to get further away for that to happen. Okay, so the ladder is falling down like this, but the base of the ladder is also coming out like that in this situation. Okay, so the variables that we're interested in here are going to be the height of the ladder and the distance the ladder is from the wall. Okay, so let's say like this is a right triangle, correct? And as that ladder slides down, it's going to continue to be a right triangle, so that's not going to change. So we can do a little ABC Pythagorean theorem here. Okay, we need to come up with an equation, some sort of equation that relates what we have in the picture with the rates that we're interested in. Okay, so we're going to start with a squared plus b squared equals c squared. Okay. Now this is the next important thing. Once you have this equation set up with whatever's going on in your picture, it's important to ask yourself what variables in this equation are actually changing as this situation unfolds. Okay? So, is A changing? Yes. Is B changing? Is C changing? No. Okay. So when I go through and I do my derivative step here, I'm only going to do the derivatives of pieces that are actually changing in the situation. Okay? So, the way that this works is, we're talking about a rate, feet per second, so everything's in terms of time, right? So, the change of the ladder as it scoots out from the wall would be dA dt, right? Because we're talking about time as it relates to time. And as this thing slides down the wall, it would be a dB dt. Change in the B per change in time. Okay? But the C, since it doesn't change, we don't need to worry about a dC dt because there's no change in C. It just stays. Okay? So, when we go through and do this, it's going to be, well, first of all, the part that doesn't change, you can go ahead and just put the number in. Now this 30 down here is a little confusing for some people because they're like, well, we know that A is 30, so why don't we just put 30 in there too? But the key is, A doesn't stay at 30. It changes, okay? So we can't put that in there immediately. We're going to work with that 30 in a minute, but we can't put it in right away because it's going to end up changing on us. Okay? But the c, since it stays the same, I just plugged in a 40 and got 1600, and I'm just going to leave it. So now I'm going to do my derivative step. So if I go through and do a derivative of a squared, I get 2a. But because I'm relating everything to time, I got to do the chain rule, dA dt. And then b, the derivative would be 2b. But b is a function of time as well, so I got to tack on a dB dt with that. And then what's the derivative of 1600? 0. So there's my derivative step. Okay, and this is the equation that I'm going to plug things into now to try and figure out my rate. Do you see how my answer is actually a variable that's in there now? What am I trying to figure out ultimately? dA dt, right? Yeah, so this question, how far is it moving away from the wall? I'm really looking for dA dt, right? How fast is A changing per unit time as it moves out? Okay, so this equation, I should be able to plug numbers in for everything else except for dA dt and then solve it for dA dt. Okay, so now it's safe to plug the 30 in because we've already accounted for the fact that it changes. So 2 times 30 times dA dt, and I got to leave that dA dt because I don't know what that is, plus 2 times b. Well, uh-oh, what's b? So remember, the a, the b, and the c, just by themselves, are the position of the ladder before things start to change. So I don't have a number for b off that picture, but I could find it, correct? Okay, if I go back to my original a squared plus b squared equals c squared, this is kind of the static situation before anything starts to change. So I can use the 30 and the 40 into there to help me get my b that I need right here. So if we go ahead and do that, we got 30 squared plus b squared equals 40 squared. So b squared would be 1600 minus 90? No, 900. So b squared is 700. So b would be the square root of 700 then. And I don't have to worry about the plus or minus in this case because everything's talking about a distance, right? So everything's positive. So I can just use positive 700. Or positive square root 700 rather, sorry. And then dB dt. Okay, now here's another thing that, bless you, gets a little tricky. It says the ladder is falling at a rate of 2 feet per second. Okay, but direction matters. Think velocity, right? If things go up, it's a positive change. If things go down, it's a negative change. The ladder's falling down. Now, dA dt should be positive because that's increasing, right? But dB dt is getting smaller. So what number should I actually plug in for dB dt here then? Because it's decreasing. -2, right. Okay. Now I just got to crunch my numbers and solve for what's missing. Okay. So 2 times 30 is 60 dA dt plus, minus 4 square root of 700 equals 0. So 60 dA dt equals 4 square root 700. I gotta go get some decimals now. So 4 times the square root of 700. Okay, and then that divided by 60. So I get dA dt equals 1.764. And what should be my unit for that? Feet per second, actually. Because dA dt, look at the way that the variable is even constructed, right? Change in A divided by change in time, right? So my unit should match that. Feet per second. Yep. Okay, got it. All right, I'm going to take this same situation. I'm going to add one little wrinkle to it. ask you another question. Let's say we got this angle of the ladder on the ground, and I want to figure out how is that angle changing as I do this. So now I'm not looking for dA dt anymore, I'm looking for d theta dt. So what is d theta dt at this moment? Okay, so since I'm looking for d theta dt, I need to figure out a way to relate theta to the stuff that I have in here. So, any ideas? Do a cosine, okay. So cosine of theta equals what? Okay, just don't worry about plugging in first though, just do the variables. A over C, okay. Right, yeah, so, but again, I want you to just write the whole thing out and then look at the equation and ask yourself what changes and what doesn't. It's just an easier way to always kind of do this. So, is theta going to change? As that ladder falls, will the angle change at the base of it? Mm-hmm. Is A going to change? Yep, we already found that, right? And is C going to change? Nope, we already talked about that too. So it's safe to plug in your C in this one already. So we've got cosine theta equals A over 40. And now I need to do my derivative step here. So derivative of cosine is negative sine theta. But then remember, chain rule, theta's in terms of time, so times d theta dt. And then on the other side, I've got 1/40th times a. So I drop the power down off of a, and it becomes a to the 0. So a is just gone. Because remember, this is really the same thing as 1/40th a, right? So you can just make it 1/40th. However, got to put the dA dt on there too, right? Okay, now again, I've got the derivative part done. This is my derivative step. And I should be able to now plug things into this. Okay, and solve for d theta dt. What's the only thing that I don't really have yet that I still need to plug into that? What theta is. And remember, theta, in this case, is what is the value of that angle before the ladder starts to slide down. So if we go back up to our original, here's where it's safe to use the 30 now, because this is at that moment it starts to slide. So we can use the 30 and the 40 in that cosine equation right here and get that value of theta for us. So it's going to be cosine theta equals 30 over 40, which means we got to do the inverse cosine of 30 over 40. And it doesn't matter if it's in radians or degrees, it's just a matter of staying consistent with it. So I'm going to do radians just because we always do that, but should work either way. So inverse cosine of 30 over 40, I'm getting 0.7227. So then I'm going to take that and plug it in here. So in this equation here, with everything stuck back in, negative sine of 0.7227 times d theta dt equals 1/40th. And we already found dA dt, right? That was from the last question, 1.764. And now we can go through and solve that thing. Find out what is d theta dt off of that equation. So negative sine of 0.7222, or 227. I get negative 0.6614. And then 1.764 times 1/40th. This is 0.0441. And this got to do a little bit of dividing here. So take that 0.0441 divided by negative 0.6614. And my d theta dt is negative 0.066, well, if I round it, 7. Okay, now depending on what mode you used, this will change. Okay, so I was in radian mode. So this is d theta dt. For me, this would be radians per second. If you did it in degrees, it would be that many degrees per second, okay, that it's changing. Another quick little check. I got a negative answer. Does that make sense based on the context of the problem? As that ladder slides, is theta going to increase or decrease? It's going to get smaller. Got a negative answer. That's good. That makes sense. So, all right. So, there's our ladder problem. Let's try a couple, do a couple more examples, and then I think we'll be good. So, let's switch gears to some spheres here. So let's say we got a sphere of water is growing larger. So that the surface area is increasing 2 pi square inches per second. So what is dr dt and dv dt when r equals 3 inches? Okay, so here's one where the equation that you're going to use is kind of dependent on the information that you have, and it's a formula from geometry you can just pull out of the front of your book or whatever. But notice how we're interested in both surface area and volume in this case. We got a dv dt down there that we're going to want to compute at some point too. Information we're given up here involves surface area. So we're going to need both of them. But let's start with just the surface area because that was in the information that was given. So surface area of a sphere is 4 pi r squared. And I was given what? What is that 2 pi? What rate is that? It's not just the surface area. It's a rate of the surface area. So since the surface area is given by S, right, that's your ds dt. Change in surface area per time is 2 pi. Okay, so we're going to need to use that. And then also keep in mind we were given the fact that r equals 3. So there's the information that we have to plug in. And first question, let's go for this. We want to find dr dt. Okay, well, we're in good shape to do that because we have a ds dt, we have an r, that's all relating s and r like this equation does. We can roll with that and be okay. So if we do the derivative here, the derivative of s is ds dt. Now the derivative of 4 pi r squared, what is that? The derivative of 4 pi r squared? Mm-hmm. And then don't forget to multiply it by what? dr dt. Yep. All right, so see how we have a ds dt and an r? We're looking for dr dt. We got it. We can plug in and do it. So ds dt, 2 pi. 8 pi, r is 3. dr dt. All right, so we got 2 pi equals 24 pi dr dt. And then if we divide each side by 24 pi, I'm going to get 1/12. So pi's will cancel, and 2 over 24 is a 12th. Okay, so it's 1/12 what? What's the unit for that? Inches per second. Right. Change in the radius per time. Radius is getting measured in inches. Time is in seconds. So there's your dr dt. All right. We still got to figure out this dv dt, which means we're going to have to pull out the volume formula for a sphere as well. Do some of the same kind of stuff like we've been doing. The volume of a sphere, we had a problem like this in your homework last night. 4/3 pi r cubed. Don't know if you have that one memorized yet or not, but don't worry about it for right now. Derivative step, dv dt. Okay, if I do the derivative of 4/3 pi r cubed, what is that going to get me? Yep, 4 pi r squared dr dt. Notice how this comes out the same as that? That's not a coincidence, by the way. We'll talk more about that later. But anyway, this 4 pi r squared, when you do the derivative of the volume, you actually get the surface area equation. That's not a coincidence. But anyway, we're not dealing with that right now. So, all right, so dv dt, we need r and we need dr dt to plug in. Can we do it? Yeah. Do we have those two things, right? Yes, we can. So 4 pi times 3 squared times a 12th. If we multiply that all together, simplify it up, it's going to end up being 3 pi. And what should be the units for that then? dv dt. Right. And there you go. We can do that one too then. All right, let's do one more here, and then I think I'm going to quit. So, do a hot air balloon one here. So a balloon is rising up 500 feet along the ground from a rangefinder, okay? So I'll quickly draw the little picture here of what's going on. So here's the little rangefinder over here, and 500 feet away, here's this balloon. That's rising up. Okay, so it's heading up, and this little rangefinder over here is trying to spot where the balloon is. When the rangefinder reads pi over 4, d theta dt is 0.14 radians per minute. How fast is the balloon rising at that moment? Okay. So what kind of geometric shape do you suppose we're going to be working with on this one? Triangles. Yeah. Just draw the picture out, take a look. Usually that's going to help you answer that question. So we're dealing with a triangle, but we're also dealing with theta, right, over here. And here's the height of the balloon. So as this balloon floats up, what's changing? The height is changing, and what else? The hypotenuse is changing, yep, and what else? And the angle, right. Okay, So now the hypotenuse in this one I don't necessarily need to work with, right? Because I've got information about how far away it is, and I'm asking a question about how high up it's going, and I have information about theta. So I just try to stick with that. What's an equation I could use to get started? Actually, no. Because the Pythagorean theorem does not include theta. I want to involve theta somehow because I got information about theta. I heard it over here. Tangent. Tangent of theta is what? H over 500. Yep. And theta and h are changing, so it's okay to put the 500 in there because that one isn't. And then I got to go through my whole derivative process here again and start plugging some things in and see what I got. But that's the crucial step, though, is getting that equation that's going to work for what the information is that you have. So, all right, what's the derivative of tangent? Secant squared x, or secant squared theta in this case. And then don't forget the d theta dt. And then this is essentially 1/500th h. So what is the derivative of h over 500? dh over dt, yep. Okay, so what in this equation is what I'm searching for? dh dt, right. So I should be able to find numbers to plug in for theta, d theta dt, get dh dt. Do I have both of those two things? What's that? That's theta, right? What's this? d theta dt, right? So I actually do. I have everything I need. So secant squared of pi over 4 times 0.14. Now in this one, remember before I said, well, if you got radians or degrees, whatever, it doesn't really make a difference. This one does, because the information that was given to you, that 0.14, was in radians per second. So you have to make sure your calculator is in radians to do this one then. So, all right, so secant squared would be just the secant of pi over 4, but then square it. So 1 divided by the cosine of pi over 4, and then square that, and that actually comes out to 2. So we got 2 times 0.14 equals 1/500th times dh dt, and 2 times 0.14 is 0.28, and then multiply that by 500. We got 140 equals dh dt. I run the math on that. And what should be my units for 140? 140 what? Take a look at what's the unit. It's feet, right? Yeah, because the other number I was using was in feet, so this had better be in feet as well. And then a double check. I always check to make sure if something's increasing, the change is positive. If something's decreasing, the change is negative. So is the height of the balloon increasing or decreasing? Increasing, so the dh dt better be a positive number, and it is. So we're good there too. Okay. All right, so you guys feeling confident with this stuff? Yeah. We can do it? All right, you can get on course sites and take a look. It should all be there for you. You got about 20 minutes here in class yet to get started.